I want to add one tricky detail with flux integrals, and it's that when you define a surface S, yeah, so this is a curved surface, whatever it looks like. So of course, when you define ds, we know that this is pointing normal to the surface. But the question is it pointing in this direction or in the opposite direction? I mean, it doesn't matter, both are normal to the surface. What will be the difference? So the difference will be that you are doing the dot product with either a vector which changes the sign of this vector ds. And changing the sign of one of the vectors in the dot product will change the overall sign of the flux. So this is like saying, what is the flux of air crossing through this surface? And the air is coming like this. So if you consider ds to point in this direction, you will get a positive flux. But if you consider ds to point in the other direction, that's also fine, but you will get a negative number as the flux. And it makes sense because your air is flowing opposite to the direction that you are considering the flux in. Okay? So the sign of the flux, you have to be a bit careful. Normally, if it's a standalone surface, you can just state, I take the positive direction as pointing away from the origin, or something like that. In other cases, you sometimes want to calculate the flux over a closed surface. Maybe I should write this. Let me do a note here. Flux over closed surface. So closed surface simply means that instead of being like a net, it's like a closed surface. I don't know, it's a surface that encloses some volume and there are no gaps. Yeah. So it's like a potato, it's like the surface of a potato. So then you want to calculate the flux coming outside of this closed surface. Yeah. So then the flux coming outside of this closed surface, to indicate that the surface is closed, we just do this symbol, we add a circle in the integral. Okay, it doesn't change anything, the calculation is exactly the same. It's just telling us that this surface is closed. So the circle tells us that S is closed. Okay, so therefore, if you calculate the flux on a closed surface, it's like saying how much air is flowing out from this volume, yeah, throughout the surface that encloses this volume. Yeah, so S encloses a volume completely. And when we do such flux integrals, we usually take the convention that ds points towards the outside. Okay, so it's like, what is the flux flowing out of the volume? If I ask you to calculate the flux flowing into the volume, then you can calculate the flux assuming that ds is pointing outside, and then just take a negative sign. Okay, because if you take ds always as pointing to the outside, so let me draw it. So ds pointing to the outside at every point. Okay, so by convention we take ds pointing outside, and therefore if I ask you to calculate the flow of air into a volume, you would have to take the negative sign of this flux integral. If I ask you to calculate the flow of air outside of the volume, then you would just take the positive sign of this flux integral. Okay. One comment is, if I use my recipe to calculate ds, will it point towards the outside or towards the inside? I don't know. You don't know until you check. So it will depend, because it will depend on what you call u and what you call v. So maybe you have two parameters, theta and phi, and you do the partial of r with respect to theta cross the partial of r with respect to phi. If you decide to do it the other way around, partial of r with respect to phi cross partial of r with respect to theta, the net result will have the same length, but it will flip sign. Okay, you know that the cross product flips sign when you interchange the two vectors. So therefore, whenever you calculate ds, look at which direction is ds pointing to, and if you are calculating the flux on a closed surface, flip it. If you see that it's pointing inside, just flip the sign of ds so that it's pointing outside. Okay, so that was it, just a quick warning of being aware of the sign of ds. Thanks for watching. Let's do some examples of the flux.